Okay, this video is part 2 of classification of PDEs. In part 1, we established the theoretical framework of classifying PDEs. This is linear second order PDEs. Before we go into examples in this video, I'm just going to start by making a quick summary of what we established in part 1. So we said for the linear PDE AUXX plus BUXY plus CUYY equal to some function P of XYU UXUY. We said the classification of this PDE depend on the sign of the discriminant. Discriminant D is B squared minus 4AC, just as in quadratics. So we said there are 3 cases which we are just going to list here. So I'm going to just tabulate this in the first column. I'm going to write the sign of the discriminant, then that is going to be followed by the type of the PDE, then in the last column I'm going to write the canonical form. Okay, so in the first case we said if the discriminant is positive, so D is positive, then the let's just abbreviate this discriminant. Let's just put sign of D here. Then I'm going to put this here because we need more space in the second column. So if D is positive, the PDE is called hyperbolic. Okay, and the canonical form is going to be U xi eta equal to f of xi eta u xi u eta. We said xi and eta are the canonical coordinates. And then if D is equal to 0, the equation is called parabolic. The canonical form is U eta is equal to f of xi eta u xi u eta. And then the last possibility is when D is less than 0. So when D is less than 0, the PDE is called elliptic. The canonical form is U, let's use U alpha alpha plus U beta is equal to f of alpha beta u alpha and u beta. All right, so these are the 3 possibilities. We are now going to look at specific examples. All right, in these examples, we are given several PDEs. The first thing we're going to want to do is to classify each PDE as parabolic, hyperbolic, or elliptic. Then in part 2, we're going to want to reduce PDE to its canonical form. Then in part 3, we're going to find the general solution where possible. We did mention in part 1, in the part 1 video, that in the cases where the PDE is parabolic or hyperbolic, it is often possible to integrate. We will demonstrate that. All right, so in this video, we look to cover A, B, and C, and then D, E, and F we will cover in part 3. Okay, so let's get on with the first one. Okay, so in part A, we have 4uxx. We're going to do this one very slowly so that we give you the opportunity to follow through all the steps. All right, so in the first case, we are classifying this. So A is 4, B is 5, and C is 1, just the coefficients of uxx, uxy, and uy1, yy. So the discriminant b squared minus 4ac is going to be b squared is 25 minus 4ac is going to be 4 times 4. So this is 16. So no, it's actually 25 minus 16. This is 9, which is clearly greater than 0. So this is telling us that the parabola is hyperbolic. Okay, according to our table here. So we're in case 1. So expect that when we reduce it to canonical form, only the uxi eta derivative, second order derivative, is going to survive. All right, so let's go to part 2 then. In part 2, we start by writing out the characteristic quadratic equation. Okay, so this equation in this case, so that equation is always given by A lambda squared minus B lambda plus C equal to 0. So just I'm sure you can remember that our A is 4, B is 5, C is 1. So the characteristic quadratic equation is going to be 4 lambda squared minus 5 lambda plus 1. So this equal to 0. We can factorize this into 4 lambda minus 1 into lambda minus 1. What it means is that lambda 1 is 1 on 4 and lambda 2 is 1. Okay, then from here we can write the characteristic ODEs. Characteristic ODEs given by dy dx equal to lambda 1. So that's the first one. And then the second one, dy dx equal to lambda 2. From here we can see that 4 dy minus dx is 0. So that means 4y minus x is a constant c1. Okay, then the second one, dy dx is 1, implies that dy minus dx equals to 0, from which y minus x is equal to a constant c2. Then from these, we say these are the characteristic curves. From the characteristic curves, we can get the canonical coordinates or variables. So the first one, xi, these are the transformations that tell us how we go from the xy coordinate space to the xi eta. Then eta is going to be y minus x. It's just these two here. The important thing with the canonical coordinates is that the Jacobian always has got to be non-zero. So let's work out derivative of xi with respect to x is going to be minus 1. Derivative of xi with respect to y is going to be 4. Derivative of eta with respect to x is minus 1. Eta with respect to y is 1. So that means the Jacobian, which is xi x eta y minus xi y eta x, so that's going to be negative 1 times negative 1. Now it's actually times positive 1 because it's this one. Then minus 4 times negative 1. This is going to be negative 1 plus 4. This is going to be 3. This is non-zero, so that is perfect. And then we need to work out our derivatives in terms of xi and eta. Now, so this is going to be based on the chain rule. So going from the xy space to the xi eta space, but xi and eta are functions of xy. So I'm just going to do an example. Partial u, partial x. So in the second case, u relates to x through xi. So that means we need to differentiate this first with respect to xi and then xi with respect to x. Then because there is a second variable, then we're going to do u eta and then eta x. In terms of subscript notation, going to be u xi xi x plus u eta eta x. Similarly, the derivative of u with respect to y then going to be u xi xi y plus u eta eta y. Right, it's exactly the same as this, but every x is going to be replaced by y. Now, so since we already have the partial derivatives of xi and eta, then working on the first order derivatives of u should not be a problem. For instance, so for the y derivative, we're simply going to take this and plug it in here, and then take this and plug it in there, and then the y derivative is done. Okay, so that means simply that the y derivative is going to be 4u xi, the eta derivative is 1 plus u eta. Okay, then for the second order derivative, we're going to have to do the same thing to each of these terms. This depends on eta and xi, that depends on eta and xi. So when we differentiate it now, with respect to, I'm just going to do this one again, sort of in detail. So we're now going to go have 4 into partial u xi, partial xi, xi partial y, okay, brackets here, partial u xi, and then eta y. So that's just from this term here, and then we're going to do the same with this term. You can see that it's this term because we've got uxi here. Okay, so then we do the same thing with this one. So it's going to be partial u eta partial xi y partial u eta partial eta partial y. Okay, then again remember eta y is 4. We've just done it here. So eta y is 4. So this one is eta y, and xi y, and then eta y is 1. Okay, so whenever we get xi, so first of all, this one in subscript notation, it's just going to be uxi, and then xi y is 4. This one is going to be u xi eta times 1. This one is 4. This is u xi eta. This is 1 u eta. Right. So this is going to be 16 u xi plus 4u xi eta plus 4u xi eta plus u eta. So when we collect terms, is going to be u xi plus 8u xi eta plus u eta. So those are the two derivatives with respect to y. Then we're going to do the derivatives with respect to x before we do the mixed one. So with respect to x, we say this is going to be u xi x plus u eta x. Now xi x is -1, eta x is -1, so both of them are -1. So this is going to be negative u xi minus u eta. Okay, then the second order derivative, we're going to have negative. When we do this one, it's going to give us a similar situation to what we had here, but this is already u xi, so that means the first one is going to be u xi xi x, and then u xi eta eta x, because the xi derivative is already here, minus, then this time we're going to have u eta xi xi x, and then u eta 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 x, and then remember both of them are -1, so we're going to have negative here into negative u xi xi minus u xi eta, take away negative u eta xi minus u eta eta. Removing brackets and collecting terms, so this is going to be u xi xi plus u xi eta plus u eta xi plus u eta eta, but these are the same, so this is going to be u xi xi plus 2u xi eta u eta eta. Alright, and then if we follow the same procedure, the mixed derivative, we are going to find that it's -4 u xi eta minus 5 u xi eta minus u eta eta. Okay, a while later we're going to sort of show you a method to keep track of these. So now what we're going to do is we're going to substitute into the ODE, so PDE. So substituting is going to give, so the PDE is 4uxx, so here's uxx here, so we're going to have 4 times that, u xi xi plus 2u xi eta plus u eta eta, then plus 5u xix xy, which is this one, so -4u is an error here, that should be xi xi minus 5u xi eta minus u eta eta, then that is followed plus uyy, which we found to be 16u xi xi plus 8u xi eta plus u eta eta. And then there is plus ux plus uy. Just go back to, there's ux and uy here. So in this context, ux, we have it here, so that's a negative minus uxi minus u eta, and then uy is 4 uxi plus u eta equal to 0. Right, and then we're now going to collect terms. So if we look at the xi terms, there's 3 of them, 1, 2, and 3. So from here we have got 4, and then from here we've got minus 20. 4 minus 20 is minus 16, then we've got plus 16 here. So that means those ones are going to cancel out. Okay, so that cancels out with that. Then we look at the xi eta terms. We've got 8 here minus 25 plus 8. So it's going to be 16 minus 25. So that's going to work out to negative 9 uxi eta. Then the eta terms, we have got 4 here. Then we have got here minus 5. 4 minus 5 is minus 1, and then plus 1 here. So that's 0. So these terms are going to cancel out. Then first order derivative terms, you can see that this term cancels out with that. And these ones are going to add up to 3, because you've got minus 1 plus 4. So that's going to be plus 3u xi equal to 0. Okay, so this, if you like, is our canonical form. If we divide by negative 9, so this is uxi minus 1 over 3 equal to 0. Now, and as you can see, only the xi eta derivative has remained. The other derivatives have all cancelled out. Okay, so this is our canonical form. Right. So that's part 2. In part 3, we are going to see if we can integrate this, and indeed we can. In this case, if we start by noting that the xi derivative is common, so we can write this equation as partial xi u eta minus 1 over 3 u equal to 0. This then we can integrate with respect to xi, and we're just going to remain with the terms inside the brackets. When we integrate with respect to xi, we get an arbitrary constant of eta, arbitrary function of eta, because this is partial integration. And then this we can integrate using, we can treat it as a linear first order ODE. The integration factor is going to be negative eta over 3. So if you multiply both sides by e to the negative eta over 3, then the left hand side is going to be an exact derivative, which then we can integrate. So when we integrate this, the right hand side is going to be an integral of e to the minus eta d eta plus a function of xi now, because we just integrated with respect to eta. Then if we make u the subject of the formula, so u is going to be e to the eta over 3 into the integral of e to the minus eta over 3 f of eta d eta e to the eta over 3 g of xi. Then this first term here is an integral of eta times a function of eta. So it's just going to be another function of eta. So we can rename it simply f of eta. And this now is the final expression of our solution, but it's in terms of the canonical variables. So what we want to do is we're going to rewrite this in terms of the original variables. So when we do that, so u of xy is going to be, remember eta is simply y minus x. So it's going to be f of y minus x plus, this is going to be exponential of y minus x over 3, and then f of xi is 4y minus x. So this is going to be our general solution. Sorry, this is g, not f. So that's going to be our general solution there. All right, so that takes us to the end of the first one. We are now going to have a go at the second one. We are going to go through this one a bit quicker, because we have taken more time on the first one, because we were explaining some basics that we want you to be to make sure that you are understanding. Okay, so for B, maybe let's start by writing out the PDE. So I've got uxx minus 4uxy plus 4uyy equal to e to the y. So A is equals to 1, B is negative 4, and C is 4. The discriminant, b squared minus 4ac, going to be 16 minus 4 times 4, going to be 0. So this PDE is parabolic. Okay. Then in part 2, the characteristic quadratic equation is going to be lambda squared plus 4 lambda plus 4 equal to 0. It's going to be lambda plus 2 all squared. So lambda 1 is negative 2. Lambda 2 is also negative 2. So that means in terms of the roots, only one root we're going to get. So that means only one canonical coordinate we are going to get. Then the characteristic ODEs is just one this time. dy dx is negative 2. So dy plus 2 dx is 0. So y plus 2x is c1. So the canonical coordinates from the characteristic ODEs, we only get one, y plus 2x. So in this case, what we do is we choose the other one to be any function such that the Jacobian is non-zero. Okay, so in the parabolic case, we choose eta to be any function of x and y, x and y, such that the Jacobian is non-zero. Typically we make this as simple as we can. So in this case, for instance, we're going to go for eta is equal to y. I'll tell you, this choice is motivated by the fact that in part B, where is the equation? Yeah, on the right hand side, we just have a function of y. Now, fingers crossed, the Jacobian is non-zero, so let's check that. Okay, so xix is 2, xiy is 1, eta x is 0, eta y is 1. Okay, so the Jacobian is going to be xix times eta y, which is 2, and the other one is going to be 0 times 1. So this is non-zero, so that means that choice there passes. Okay, then after that we're going to use the chain rule to find the x and y derivatives. So this time we're going to go through this a bit quicker because we've already dealt with the details in part A. So ux is going to be u xix plus u eta x. Xix is 2 here, eta x is 0, so the second term vanishes. Then uxx, if we do the same routine, it's just going to be 4 times u xi. Then we go to the y derivative. So uy is going to be u xiy plus u eta y. Xiy is 1, eta y is 1. So this is going to be just u xi plus u eta. Then if we go to the second order derivative, we are going to find that this one is u xi plus 2 u xi eta plus u eta, and then the mixed derivative uxy is going to be 2u xi plus u xi eta. Okay, and then we're going to substitute into the PDE, which is this one there. So substitute into the PDE. So the PDE is uxx minus 4uxy plus 4uyy equals e to the y. Okay, uxx is just here is 4u xi, and then the mixed derivative is just here 2u xi, and the y derivative is there. So that one is u xi 2u xi eta u eta eta, and then the right hand side is e to the y, which we can simply write as e to the eta, because we've chosen eta to be y. Now let's look at the like terms. So xi, we've got 4 here, minus 8 there, plus 4, so that cancels out. Then the yeah, I think there is an error here with the x term. Oh no, it's fine, it's fine. Okay, then the xi eta terms, we have got negative 4 here, yeah, just one moment. Xi eta terms, all right, so actually there is a minor correction here. This must be 2, so that is going to make that 1 2 there, and then the xi eta terms, there is a minus 8 here plus 8 here, so the only term that's going to survive on the left hand side is the u eta terms, and there's 4 of those. So this is our canonical form for this equation, which is the canonical form. Then in terms of part 3, we can integrate this easily with respect to eta. So let's start by taking the 4 to the right hand side. 1 over 4 e to the eta. So we will integrate this once with respect to eta. We can integrate e to the eta with respect to eta. We get exactly the same thing, but there's going to be a function of xi. Then integrate again. This becomes u. This is still e to the eta. This is a constant as far as partial integrating with respect to eta is concerned. So it's going to look like that, and then we're going to have another constant of xi. And then that's our solution in terms of the original variables. The solution u of xy is 4e to the, remember eta is y, then y here, then xi is what was xi here? Xi is y plus 2x plus g of y plus 2x. So that is going to be our general solution. Okay, I think we're going to stop this video here. Then we're going to continue in part 3 with the other questions from C and going onwards. Thank you. Hopefully this has been useful. If it has, please do subscribe so that you can get notified whenever we post new material.